So a precursor to compactness as we saw it is Bolzanovi's trust theorem, telling you that every sequence has a convergent subsequence. And there is indeed a similar definition of a notion called sequential compactness, whose conclusion is the conclusion of Bolzanovi's trust theorem. Namely, if we take a topological space, we say X is sequentially compact if every sequence Xn in X has a convergent subsequence. Okay, so not sequentially compact, sequential compact, but sequentially compact if every sequence in X has a convergent subsequence. Okay, so we want to say that what is the relation to compactness. So first of all, let's assume X is compact. Yeah. So the lemma is that any infinite set A contained in X has an accumulation point. Okay, so recall something is an accumulation point means that it has a neighborhood which does not intersect any point in X other than so being an accumulation point means every neighborhood intersects A, and not merely that, it doesn't, if little a, the accumulation point is in A, it intersects A in a point other than A. So not having an accumulation point means each point has a neighborhood which is either, if little a is not in A, it just does not intersect A, which will tell you that the complement of A is open, or if it is in A, then it's a single point A, which will tell you that by the subspace topology, little a is open. Okay, so else A is closed, and a point in a set not being an accumulation point tells you it's isolated, and so this means it's discrete. Okay, so points of A, so let me say singletons form an infinite cover. Without a finite subcover. Okay, so we always have an accumulation point. So sequence will have accumulation points, but to convert that to convergent subsequence, we need a countability condition. Yeah, so if X is first countable, is compact, just saying it again, and first countable, then X is sequentially compact. First of all, if Xn, if the sequence has finite image, this is a priori possible, but that's only possible in only one way. Then it has a constant subsequence. Yeah, so if it takes only finitely many values, it must take at least one of them infinitely many very often. Okay, so any constant sequence is convergent. So else the set Xn has an accumulation point. Let's call it X infinity or something. Okay, and with neighborhood basis, let's take, so it has to have a countable neighborhood basis, u1, u2, un. Okay, so by definition of accumulation points, as X infinity is an accumulation point, oh sorry, this goes on, it's not finitely many, so un onwards, accumulation point. Okay, for all n in n, what we'll do is, this is the same proof as sequential closure. So for all n in n, there exists nk such that let's call it capital N in N, such that X and K is in U1 intersection all the way up to UN. Okay, so we see the subsequence X and K will converge to X infinity. Namely, given X infinity and given any neighborhood of it, this neighborhood contains contains a neighborhood basic element, so some UN, which also contains the point X infinity, and so it's contained it contains the intersection up to that n. Yeah, so given anything, so if we look at any neighborhood V, then you can find a corresponding basis element UN, and then not just that X and K, but all subsequent ones by construction are actually contained inside this set. So we can see that X and K converges to X infinity. So this means that if we have, so putting the thing, so this actually proves the theorem. So if it's compact and first countable, the sequence has an accumulation point or a very simple case, and there is a convergent subsequence. So the other direction is more useful because it's often easier to work with sequences to prove compactness. But so now suppose X is sequentially compact. Okay, and for right away, so theorem, I can as well state it as a theorem. Suppose X is sequentially compact and second countable. Then X is compact. So here's the proof of this. So suppose, so let's take, let U alpha in A be an open cover, and now we use Lindelof's theorem. So we have an open cover, and that's where by second countability so let's call it script. U has a countable subcover, and we'll find a finite cover in here, subcover. Let's say V1 equals U alpha 1, V2 is U alpha 2, etc. So I'll just call them V1, V2, Vn for convenience. So we have a countable subcover, and now that we have a countable subcover, we are actually going to construct a finite cover using sequential compactness. Okay, so for that we will show, so we'll consider a couple of cases. So the idea is that if you have a countable cover, we can take cumulative unions, and we want to say at some finite stage they cover everything. Okay, so let us look at the complement of this cumulative union. So let Fn is the complement of union I equals 1 to n of Vi. Okay, so if Fn is empty for some n, then V1, Vn is a finite subcover. That's what we wanted, of the Vi's and hence of the original Ui's. Else, what we know, we have is that Fi are closed and F1s contains F2. So they're closed, they're non-empty, and F1 contains F2, which contains F3, etc. And compactness, sequential compactness will tell you, so claim is that intersection of Fi, I is 1 to infinity of Fi is non-empty. Okay, so this will contradict proof. We'll see what it contradicts in a moment. So so each Fi is non-empty. Yeah, so pick Xi in Fi and consider by sequential compactness a convergent subsequence. X and K converges to x infinity of xn. Okay, then we claim that then x infinity is actually in intersection I equals 1 to n of fi. That is because for each fi, this is a decreasing sequence as x and k is eventually in fi for all I. So FIs are a decreasing sequence. You have this set and they're getting smaller and smaller, and we are picking points in them. And then further we are passing to a subsequence. So any point in the subsequence is eventually inside each FI, and FIs are closed, and hence any limit will also be inside this FI. I mean inside the closure of FI a priori, but FI are closed. So x infinity is going to be in FI for all I, so it's an intersection of FI. So that means FI is non-empty, but intersection of fi I equals 1 to infinity is x minus the union I equals 1 to infinity of vi, which is x minus x, which is empty. Okay, a contradiction. We are simply contradicting the fact that this is an open cover. Okay, there are various ways to arrange this proof, but we have used essentially the closed set criteria. That is, if we have a sequence of closed sets so that every finite intersection is non-empty, then the full intersection is non-empty. But we proved this just for sequence using only sequential compactness, provided your collection of sets is countable. Otherwise, sequential compactness would be compactness. It's not. We can prove the weaker version of this where we have only countable covers, but second countability let us pass to countable sequences of closed sets, but second countability let us pass to the closed sets. Second countability let us pass to the countable subcover.